Okay, so let us begin our class 11 tutorial. So it's saying the ground state energy of hydrogen atom is E1 equal to minus R, where R is this value is called the Rydberg constant. If the atom makes a transition from an excited state n equal to 3 to the state n equal to 2, then the radiation emitted would be how much energy in electron volt. So we can solve it here, it will not be too long solution. So we know for hydrogen atom there is this formula of energy, that energy levels are this En equal to minus R divided by n square, where n goes from 1, 2, 3, etc. So R is a Rydberg constant, which value is 13.6 electron volt. So basically your energy levels are defined as En equal to minus 13.6 by n square electron volt, right? So it's minus 13.6 by n square electron volt. Now if that is the case, then you know that your energy levels out between which the transition is happening is from n equal to 3 to n equal to 2. So n equal to 3 to n equal to 2, the energy difference is what is radiated by this transition will be the energy difference between the two levels. So this is E3 minus E2 minus 13.6 by 3 squared minus and minus plus 13.6 by 2 squared. So this is 13.6 1 by 2 squared minus 1 by 3 squared, which is 13.6 to 1 by 4 minus 1 by 9, which is 13.6 into 5 by 36. If you calculate, it will be around 1.88 electron volt. So this is your answer in electron volt, how much energy will be radiated by this emission or emitted. So this is 1.88. So and the answer you can see it's between 1.8 to 1.9. So our answer is correct. So this is done. Then question number 2 is the allowed angular momentum J when we add two particles with angular momentum J1 and J2 with 5 by 2 and 3 by 2 are what? So here also we can do it here, that when you add two particles angular momentum, basically, so you know that the allowable values will be, there is this formula that allowable values will of the net angular momentum by the combination of two particles will be from mod of J1 minus J2 as a minimum up to J1 plus J2 as a maximum. So here because you see that you have to take a modular sign, so it's not a negative value. So you have J1 as 5 by 2 and J2 as 3 by 2. So you take this up to their addition, that is 5 by 2 plus 3 by 2, which is like 1 to 8 by 4 is 8 by 2 is 4. So 1 to 4. So the values can be 0, sorry, not 0, 1, 2, 3, 4, because this will be all in the difference of 1 as the value of J goes like. So the accepted answer is C. 1, 2, 3, 4, these are the allowed values, and you can define its range by this formula, that it will go from mod of J1 minus J2 up to maximum J1 plus J2. Okay, so now question number 3 is the matrix element of Z between 4f and 4d. Hydrogen states is given by this, and the value is given in terms of A0, where A0 is the Bohr radius. Then you have to calculate, if you take instead of 2, if you take m equal to 3 here, and instead of Z there is y, then what will be this value in terms of A0 again. So this needs a sort of elaborated thing, but we'll solve it here. So the thing that is given to us is some 4f with m equal to 2, then z 4d m equal to 2. Okay, so now these position coordinates x, y, z, these are all position coordinates, right? So they can be represented in terms of the angular momentum wave function part, that is y-lm sort of thing, that can be represented like that, or also spherical tensor of rank 1. So these x, y, z position coordinates can be represented by y-lm, this part which is the angular part of the total spherical uh, coordinates and wave function quantum mechanics. Also they can also be represented as spherical first rank tensor, which is T1. Now the value here can be varying on the value of m, it can take any value, but 1 in bracket means that this is a tensor of rank 1. So basically first rank tensor, you know that that is nothing but a vector, or you can, in general terms, you can say this is a first rank tensor. So this is the thing. Now you know that in position coordinates, simply you know the form, that z equal to r cos theta, then y equal to r sin theta sin phi, x equal to r sin theta cos phi. So these are all the position coordinates defined for spherical coordinate case. Okay, spherical coordinate system, the xyz can be represented by r theta phi like this. So from here you can guess that okay, your z has only cos theta term, right? So cos theta is something that appears for y 10. Okay, so cos theta is something that appears for y 10. If you check out the angular momentum uh, wave function forms, you will see that y10 has this cos theta expression in the functional form. Similarly, your x and y are in the form of r sin theta e to the power of plus minus I phi. Now depending on the combination of x and y, sometimes it is sin phi and sometimes it is cos phi, right? So but in general terms, this is a dependence like this. So this sin theta and e to the power I phi sort of a term comes for y 1 plus minus 1, where L equal to 1 and M equal to plus minus 1. So this if you look at this form, this appears to have a form of this. So which is in turn related to the position coordinate of x and y. On the other hand, y10, where L equal to 1 and M equal to 0, this is related to the position coordinate of z. So if you go like this, then you see that uh, the first thing you can represent this, like this thing you can represent as a spherical tensor also of rank 1, that will go like t bracket 1 means rank 1, and then plus minus 1 defining the m value. Okay, then what will be the case is that, okay, so the first form that we wrote down is that are given in the question, 4f m equal to 2, z 4d m equal to 2. Now here 4f means SPDF, so here L equal to 0, 1 to 3. So here L equal to 3, M equal to 2, and then Z, and then this is D is SPD, so L equal to 2, M equal to 2. Okay. So here this you said, you saw that this is related to L equal to 1 and M equal to 0. In other terms, this is T1, 0. So this can be deconstructed as L equal to 3, M equal to 2. Now only take the terms in M. So for Z the M is 0, so this we say as M1, and the second term we call as M2. So M1 equal to 0, M2 equal to 2. Cross or multiplied something. So this is the rest of the terms that is dependent only on L not on m, so this is L equal to 3, and then this z term has tensor rank 1, so here L equal to 1, and then on the last term L equal to 2. Okay, so now you can see that the rule of selection rule, if you see, selection rule says this kind of a m2, m1, m2 will only be non-zero only if m1 equal to m minus m2 or m equal to m1 plus m2. Only then it will be allowed or will give a non-zero contribution. So here you can see that your m equal to 2, m1 and m2 is 0 and 2. So 2 equal to 0 plus 2, so this condition is valid. That means this will contribute and give a non-zero value. Now this value, if you are familiar with the CG coefficient or Clebsch-Gordon coefficient, you will find out. So I am not going into the detailed derivation, but the idea is that for such a combination, the CG coefficient value, that is known to be 1 by root over of 3, right, cross the whole other thing that is not dependent on m anymore. So this is one part. Now on the second part of the question, you are given another term which is like this: 4f m equal to 3 y 4d m equal to 2. So this basically means second 4f means L equal to 3, m equal to 3. And why this thing you can represent, because I already told you that x and y can be represented as tensor rank 1 and then m equal to plus minus 1. So for y m, so the combination has to be written down basically, because you can see that r sin theta, or for x minus iy, this is minus, so this is r sin theta e to the power plus minus I pi. So this is the case. That means whatever is the tensor representation that will be given, that has a form like this. So this t1 plus minus 1 has a form like this. So for y, you have to basically take a linear combination of both. That means y will be, there is a particular thing that y will be this form: y by root over 2 y1 plus 1 minus, sorry, plus t1 minus 1. Okay, so if that is the case, that you replace it here, that this is I by root over 2 t1 plus 1 plus t1 minus 1, then L equal to 2, m equal to 2. So here you see I by root over 2, L equal to 2, L equal to 3, m equal to 3, and then you have the tensor rank 1 with plus 1 as m. So here m1 equal to plus 1, and from here m2 equal to 2. Okay, cross the other term which is only dependent on L, so L equal to 3, then T only 1, and then L equal to 2. This whole term plus there will be the terms coming from this other term. Okay, so this will have L equal to 3, m equal to 3, then m1 equal to minus 1 because this is minus 1, m2 remains as 2, cross L3 t1 L2. This whole thing under bracket. So this we are getting that this is I by root over 2. So this part you see that your m is equal to m1 plus m2 because 3 equal to 1 plus 2. So m equal to m1 plus m2 is valid. So this will contribute. This is correct. And this value will be basically 1. So the CG coefficient value equal to 1 and non-zero because this is allowed from the selection rule is valid. So this value is you are taking as 1 cross this whole L term plus here you see that m equal to 3 and on the other hand you have minus 1 plus 2 which is plus 1. So this is not equal. So m not equal to m1 plus m2, that means selection rule is violated for here. So this will not contribute. This will give rise to 0 value. Selection rule is violated. So you cannot take this value. This value will go to 0. So this is 0. So only you are left with I by root over 2 into 1 into this factor that we say as sum bracketed form, which is basically this factor. Now you see that what you had from the earlier case is 1 by root over 3 into the same factor, and right now from the y in between you are getting the same factor times I by root over 2. So if you take a ratio of, let's say 1 and let's say this is 2. So on the left hand side you had this term, right? So you can use that. Third, 1 by 2 ratio 4f m equal to 3. You take 2 by 1 instead. So 4m m equal to 3 and this was y, then 4d m equal to 2 divided by 4f m equal to 2 and z 4d m equal to 2. So this is equal to I by root over 2 into 1 by 1/3, 1 by root over 3. So this term you have to calculate. So this is 4f m equal to 3 in terms of a naught you have to get it, right? So you already know their ratio and you know the denominator, which is basically this term that is given already in the question. So this term value you know, so you would substitute that here. So on the right hand side you have this term coming up, so which is minus root over of 2 by 3 a naught. So this and this and this and this cancelling out, so this is minus I times a naught. So this is your final answer. Okay, so we are getting our answer as minus I a naught, which is this. Now question number 4. The product of the position vector component xy in terms of the spherical rank 2 tensor, that is T bracket 2m, will be what? So earlier question we were dealing with spherical tensor with rank 1, so bracketed term was in 1, but here you have rank 2 tensor, so this is 2. So how to represent that? So there is a specific form so of this rank 2 spherical tensors, which is okay, let me write down. So these are rank 2 tensors, so these are basically coupled form of two rank 1 tensors. This is the idea. So if your tensor rank 2 has to be written down, so that is basically sum over m1 m2 l m1 l m2, then here l is will be sorry not L, this will be 1 because that is the rank that we are defining. So this is 1 M1 and then 1 M2. Then here rank is 2, so this is 2 M and then R M1 R M2. So here what was the question is that T2M, you have to use this and you have to express this XY component. So in the options you can see all of them has the m values as either +2 or -2. So basically you see that for this rank of tensor second rank, so m value is either +2 or -2. So the net m to be either +2 or -2. Let's say for now like m as +2, then the selection rule says that m equal to m1 m2 has to be satisfied. So the only possible combination is both m1 equal to +1 and m2 equal to +1. So if that is the case, then you see that you have T2 m equal to 2, where you have this is equal to this part. Then because here this will be 1 and 1 and here it will be 2, so the selection will be satisfied, and this is a CG coefficient whose value is 1, so this will be 1, so no need to take that. And then this is RM1 and RM2, so this is 1 times RM1 is R plus 1 and RM2 is again R plus 1, so this is R plus 1 squared. Okay, so then you have R plus 1 equal to R plus 1 squared is basically 1 by root over 2 x plus iy whole square. So this has a form like this, that this can be represented as x plus iy by root over 2. Anyway, this you can relate because you saw that x equal to r sine theta cos phi and y equal to r sine theta sine phi. So from there you can say somewhat relate that this is coming from a relation spherical coordinate like this. So after that you see that your r T2 2 is this which is half I square y square is minus y square plus 2ixy. Similarly for T2 but m equal to -2, your combinations are m1 equal to -1 and m2 equal to -1. So this will be like r minus 1 whole square, which will be like 1 by root over 2 x minus iy whole square, which is half x squared minus y squared minus 2i xy. So from here you see that your T2 rank 2 with m equal to -2 can be written down with this form and this form. So simplify from 1 and 2, you will get your xy, because you see that 1 minus 2 is basically I xy, because this 2 and 2 cancels out, minus minus plus I xy. Okay, so rest of the terms will be cancelling out because they are equal, and the right hand side you have 2 minus 2 minus 2. So you have xy 1 by 2i, this thing. So this is basically I, if you take that I up, so this is minus I by 2. Final answer is, this is rank 2 m equal to +2 minus rank 2 m equal to -2 is equal to your xy. So this is xy in terms of the spherical tensor of rank 2. So you see that your answer is A. Okay. Now, question number 5 is the maximum degeneration of states when you add angular momentum J1 equal to 4 and J2 equal to 2 is 1. So, when you add this J1 and J2, you see that your J1 is actually greater than J2 because 4 is greater than 2. So in such cases, the degeneracy will be decided by which one is a smaller factor, and then you know that for a certain value of J, the possible values of Mg will be 2J plus 1 times, right? So for any J1, you will have 2J1 plus 1 number of Mj1 values, and for any J2, you will have 2J plus 2 Mj2 values. But because you have to say what is the degeneracy of states, then obviously you have to take or go with the smaller term, because that will give rise to degeneracy rather than the higher term. So degeneracy count equal to number of possible Mj values for J equal to J2, since J2 is less than J1. So if your J2 would have been greater than J1, then you have to go with J1 because that is a smaller value. So in this case, you have to go with J2 because that is a smaller value. So the count is 2 J2 plus 1, and J2 is basically mentioned in the question as 2. So 2 into 2 plus 1, so that is 5. So the degeneracy count is basically 5. Okay, now question 6. Consider a state vector of this kind of thing. The possible measurement of square of angular momentum operator on the state 2 minus 1 is how much? H cut squared. This is also a short question. We can solve it here. You see, on the state you have to deal with the operator L squared. You have two states, that is L and M value. L and M value. Here L equal to 2, M equal to minus 1. Here L equal to 1 and M equal to minus 1. But the state on which you have to work on is 2 minus 1, right? So you know that this L square operator has eigenvalue like this, L into L plus 1 each cut squared. Okay, so then L square, when it operates on 2 minus 1 state which has L equal to 2, it will give rise to 2 into 2 plus 1 each cut square, which is 6 each cut square. So the answer will be 6, which is also true. So now question number 7 is that two atoms with angular momentum J1 equal to 2 and J2 equal to 1 are coupled and are described by a Hamiltonian epsilon J1 dot J2, where epsilon greater than 0. If the Hamiltonian acts on capital Jm state, when the energy eigenvalues corresponding to the possible values of the total angular momentum J will be what? So first of all, if J1 equal to 2 and J2 equal to 1, so then what are the possible combinations of J? So J can go to mod of J1 minus J2 to J1 plus J2. So it will be like mod of 2 minus 1 to 2 plus 1, which is like J goes from 1 to 3, which is in the gap of 1. So this is 1, 2 and 3. These are the possible values of the net J, right? Now you have energy equal to epsilon J1 dot J2, right? So you can express it like the total angular momentum J equal to J1 plus J2. So J squared equal to J1 plus J2 whole squared, which is J1 squared plus J2 squared plus 2 J1 J2. So J1 dot J2 will be J squared minus J1 squared minus J2 squared divided by 2. So from here you can write that your Hamiltonian, so this is still question number 7 ongoing. So Hamiltonian equal to plus epsilon J1 vector dot J2 vector, which is epsilon okay. So now this thing, if this is there, then what will be the eigenvalue when it operates on a capital Jm state? So this is epsilon by 2 common, and this is J squared on Jm is J into J plus 1, each cut square is taken as common, minus J1, J1 plus 1 minus J2, J2 plus 1. Epsilon naught A epsilon h cut square by 2 uh, J into J plus 1 minus J1 and J2 values are known. So J1 equal to 2 and J2 equal to 1. So this is 1 into 1 plus 1 minus 2 into 2 plus 1, which is epsilon h cut squared by 2 J into J plus 1. Okay. Now this is your final answer. Now based on what is the value of j that is taken, because j can take the values of 1, 2, 3 all. So for j equal to 1, energy is this eigenvalue, which is epsilon. So for j equal to 1, this is 1 into 1 plus 1. So this is 2 minus 8 is minus 6. So this is minus 3 epsilon h cut square. For j equal to 2, equal to epsilon h cut square by 2. 6 minus 8, so this is minus 2, so this is minus h cut square, 7 h cut square. J equal to 3 is equal to 3 into 3 plus 1 is 12. So this is 2 epsilon h cut square. So the values are minus 3 epsilon h cut square plus minus epsilon h cut square and plus 2 epsilon h cut square. So the values are option number A. Now question number 8 is that the Claes Gordon coefficient m1 equal to 1, j1 minus 1, m2 equal to minus j2 plus 3 and j equal to j1 plus j2 m will be non-zero if. So this is a very useful terminology or property of CG coefficient, that this coefficient value will only contribute or will be non-zero only when this coupled will be non-zero or contribute only when m1 plus m2 equal to m. So here m1 equal to j1 minus 1, m2 equal to 3 minus j2, which is, so this is j1 minus j2 plus 2. This is the allowed values of the m for the CG coefficient to be non-zero. j1 minus j2 plus 2. So this is our correct answer. Now question 9 is again pretty simple, that the parity operator P anti-commute with the orbital angular momentum L that you have to show. So this kind of thing we have seen earlier, that if your parity operator is P, your angular momentum operator is L, and it is acting on a state psi r, and if it is LPL equal to LP psi r, then you say that P and L has commuted or combined with each other. So PL minus LP equal to 0 and PL equal to, okay. So and if it is no, not the case, then if it is sure true, then it will commute and if then they anti-commute. Now you know that angular momentum L operator is basically r cross p, linear momentum and linear position. So you have first PL acting on psi R is basically parity operator, so changes all R to R and P to minus R to minus R and P to minus P. So when this acts on psi R, this becomes P. So this is equal to this. Now when parity operator acts on the whole thing, it changes R to minus R and P to minus B, and then psi R to psi minus R. But this minus and this minus absorbs with each other, so this is R cross P psi minus R. So this is basically L psi minus R. Now what will change psi R to psi minus R is only P. So P directly acting on psi R is giving you this. So you are getting PL equal to LP, or you say PL equal to 0. Not anti-commute. So the statement is false in the question that they will anti-commute, but rather they will commute with each other because PL equal to LP. So this is a false statement. Now the last question is that a beam of particles is subject to a simultaneous measurement of angular momentum variables L square and Lz. The measurement gives pairs of values L equal to m equal to 0 and L equal to 1, m equal to minus 1 with probabilities 3 by 4 and 1 by 4 respectively. Then the state of the beam immediately before the measurement can be written down as what? So here also you can see it here that from the solution you are of by the operator L square and Lz, you will only get L and M information, right? So here you are getting L equal to M equal to 0 one state and L equal to 1 M equal to minus 1 as another. So now the probability is saying as 3 by 2 and 1 4. So you know the amplitude is root over of probability. So our initial state can be, the probability is here 3 by 4, that means probability amplitude is root over 3 by 2, and for 3 by 2 this is 0 0. So this is the case that sorry, I made a mistake, that there's a technical glitch. So this is 3 root over 3 by 2 1 0 plus half, because this is 1/4 as a probability, so the square root is probability amplitude. So this is for 0 0 it is root over 3 by 2, and for 1 minus 1 this is this. But now there is also another phase factor coming. So anything, any wave function can have a phase shift like this. So you can take this phase factor as, on the second term as half e to the power I alpha 1 minus 1. So essentially we are getting A as a correct answer. But if you look at this because this I alpha to the power I alpha is a relative phase, so it can be on either of the terms. It can also be on this term, and this term can can have no phase. But actually basically because this is all a relative phase concept, so it does not matter whether you put the phase or here or here. But what matters is standard means say that the phase factor introduced on the later terms, not on the first term. So that is why uh, we are getting this answer as our final answer. So this is this. So with this we have solved all the questions in week 11. We'll next see week 12.